Poincaré's last theorem sparked interest in symplectic geometry, especially the Arnold conjectures from the 70s. Arnold conjectured a lower bound for the number of fixed points of a symplectic map, which comes from a Hamiltonian dynamical system. So in the case of the annulus, this is a manifold with boundary which has Betti numbers 1, 1, so the expectation is to have two fixed points, and in general, if you have Betti numbers bk, one can conjecture that this is the lower bound for the number of fixed points. Arnold was making a stronger statement in terms of the number of critical points, Morse critical points, and the Morse inequality shows that the weak conjecture is really weaker, but there are other versions where you make also less assumptions on the fixed points. The fixed points can be degenerate, and then one expects less, like the number of critical points, for a non-Morse function can be less, and also the category is a lower bound, believed to be a lower bound, or the cup length, which is a homological notion too. So this is an interesting theme because it involves different parts. It involves Morse theory, dynamics, and also here's a topology, Lustenich-Schneermann theory. So the conjecture itself has been kind of verified by Arnold, kind of just near the identity, and so maybe that was also a reason for the conjecture. And then it has been generalized and proven in certain cases, especially by Fleur. So there was a whole cohomology theory was invented, and I think it is now considered proven, the weak one, and so there are several works which have done that. There's also some critique, like MacDuff and Ryan, they have kind of also pointed out that technicalities are, might have to be smoothed out a little bit. There are other approaches like Hofer, Wysocki, Zender. So there are different theories built to kind of understand this number of fixed points. So that's an interesting thing. So for me, kind of I'm spitballing here a little bit. Wouldn't it be nice if one could just prove this from a quadratic Lefschetz fixed point theorem? So the usual fixed point theorem tells that the number of fixed points is equal to the induced map on cohomology, the trace of the supertrace of the induced map on cohomology. Supertrace, and supertrace means that we have positive and negative cases. So if you look at the quadratic case, there is a possibility that these odd Betti numbers are, the induced map on the odd cohomology is just flipping things around. But I don't know, and I was actually kind of also puzzled a little bit, how do you actually test this? So if you want to have a kind of a discrete version of a Hamiltonian system, so you have to kind of say what you do. You want a finite set, right? And you want to have a map on this finite set, and you want to say what it means to be symplectic. You want to say what it means to come from a time one map from a Hamiltonian system, and you want to have actually interesting cases and reflections. But there is a dihedral symmetry, but in general, if you look at a manifold, and there is no symmetry, so you cannot just take endomorphisms or simplicial maps. So there are different approaches to tackle the continuum using finite maps, and one of them is the Brouwer simplicial approximation theorem, which however doesn't seem to be well suited, because you have a map from the barycentric refinement to G. You cannot find a simplicial map which covers the map which you are interested in. there are other approaches. In the measure preserving case, you can cut things up more freely, and then there's a cut-off step in approximation theory, which is very nice and useful in dynamical systems. Intriguing theorem which I myself have tried, of course, when I was working on the standard map, is to use finite map to approximate a map on a torus. So if you have a map on a torus, you can approximate it with a permutation. That's Lach's theorem from, I think, 72, and this is, but this is not a simplicial map. Even you make simplices, if you kind of cut it into simplices, that's not a simplicial map. So it just permutes the simplices, and there is no kind of these squares have been together initially. They might, they're in general not together anymore. I think, however, it's a perfectly fine setup for the Lefschetz fixed point theorem. You don't need even any regularity. A situation where you approximate a homeomorphism by a permutation of a finite set of simplices. So that's pretty cool, and the Lefschetz fixed point theorem works in this case, and also the quadratic Lefschetz fixed point theorem works. The question is just what happens in the quadratic case, and there are kind of some difficulties here, or things which are not resolved. So another approach which I have kind of looked at, especially I made a little video here in 2021, almost 3 years ago, where I thought that the kind of looking at wave equations is the right thing to do, to approximate, instead of having a discrete map. We just take a continuous quantum mechanical map, and we are using this, and then we can see what happens there. That's also very physical, because in nature particles move like waves. Another approach is kind of just from the numerical point of view, or what my advisor Landford was interested in. When you have a computer and you look at a homeomorphism or a map, and you study it, then of course this is just a permutation of a finite set of points, a map on a finite set of points, because the computer has only finitely many points. So the machine precision here plays a role, but you can play with this with any h. You say, okay, this is my accuracy, and then you cover the manifold with enough points. You don't care whether the manifold is whether this discrete graph which you get is a manifold or not. Like here, actually, this is kind of a very simple case where we have a one-dimensional circle, and I just took 4 more points, right? So it's no more a manifold. So that's, but it's homotopic. So this is an interesting theme. You approximate a given manifold with something which is homotopic, and which is more natural, in the sense that if you are studying it numerically, then that's what you are looking at, and that's the Vietoris-Rips approach. And in this case, I mean, one can also look, this is kind of an interesting case where you also can look at the cohomology. So there is the zeroth cohomologies for any graph. It's just a constant function on the vertices, and then you have the H1. In this case, you can write down this is the connections. So some connections have a value 2, and other connections have a value 1. So that is a harmonic form. When you write down the one form Laplacian, that's in the kernel of the one form Laplacian. And then you have also triangles. So on the triangles, there's no cohomology there. So you don't care whether we introduce higher dimensional stuff. The cohomology is trivial there, and you, I mean, in the simplicial case, if it's homotopic, then the cohomology is the same. So if you look at the induced map on the cohomology, it doesn't matter whether you have kind of a manifold or something homotopic. Do it. And then I mean, one of the interesting things and to investigate, be nice to have numerical results, is to take a Hamiltonian map, or kind of say a torus map, which has, you know, the center of gravity 0, like Arnold was suggesting, and where you have 4 fixed points, and then see whether you have really 4 fixed points for the discrete map. I bet it is, and I bet it works to take a discrete version of a map on a 2-dimensional torus, and which preserve the center of gravity. You don't want to just translate, that doesn't give any fixed points. But Arnold already in his appendix pointed out that this case you have 4 fixed points. It's an interesting theme already for the 2-dimensional torus. A roommate of mine, also a grad student, Martin Flucher, has worked on kind of the case of homeomorphism, which is not diffeomorphism, homeomorphism, which is harder. So torus maps, and there was a theorem of Frank's which give 2 fixed points, and so there is in the diffeomorphism case, there's Conlade-Sender have proven that there are 3 fixed points, but one thinks that there actually are 3 fixed points because the torus has Lusternik-Schniermann category 3, minimum number of critical points is 3, and the cup length is 3. As far as I know, this is kind of still unresolved whether there is a 3rd fixed point for homeomorphism. That's it for today.